Hi guys, happy Monday. I hope everybody's doing well and you had a good weekend. Hopefully everybody completed 7.4 and the worksheet and understands Le Chatelier's principle and is working on the virtual lab, which is due on Tuesday. Okay, so we're going to start off with 7.5 today. So this is going to be, there's going to be a lot of math in this lesson, so make sure you have a calculator that has like a scientific calculator. So using the square root button because we're going to be using the quadratic formula today. Okay, so the first thing we're going to talk about is the reaction quotient, which is called Q, and it's calculated by substituting in initial concentrations of the reactants and products and seeing where the chemical equation is along the equilibrium. So if you find out that the concentrations given give you a value for Q that's greater than K EQ of the system, that means that the equilibrium is way on the product side and it needs to proceed from right to left to reach equilibrium. If Q is at equilibrium, KEQ, that means the system is at equilibrium. If Q is less than KEQ, so C and EQ are the same thing, by the way. If Q is less than K, that means the system right now is lying to the left in the reactant side, and it needs to go to the product side to reach equilibrium. Okay, so this kind of shows you what I mean. Okay, so if Q is less than K, the reaction is in the reactant side and it needs to go towards the product side to reach equilibrium. If they're equal, that means nothing has to happen. And if Q is greater than K, that means it has to push towards the reactant side to go back to equilibrium. Okay, so we're going to do an example. Nickel 2 oxide can be reduced to the metal by treatment with carbon monoxide if the partial pressure of CO is 100 millimeters of mercury and the total pressure of CO and CO2 does not exceed 1.0 atm. Will this reaction occur at 1500 K at equilibrium? And your K pressure is 700 atm. Okay, so you're given some values and then you have to plug it into the equilibrium expression. So remember, you can use pressure units when you're plugging in to find where along the equilibrium you are. So here we're working with pressure. So we're going to put in CO2 is our product. So we're going to put it on top divided by a reactant, and we get 6.6, which as you can see is way less, or sorry, way less than the Kp that's given. So because it's way less, it's going to proceed to the product side. Okay, so that's it for that section. So we're going to now move on to an example showing you. So I split up the examples to show you scenarios. So scenario number 1 is square rooting both sides. So here you want to fill in the double-headed arrow here. H2 plus F2 is forming 2HF, and they're giving you the KEQ value. They gave us 3.000 moles of each species is put in a 1.50 liter vessel. What is the equilibrium concentration of each species? So first, we're going to have to figure out the initial concentration to put into our ice chart. So we're going to have to do 3 divided by 1.5 to get the concentration. Okay, so this is shown here, and you should get 2.000 moles per liter. This is a big M here to represent moles per liter, so that's going to be our initial concentration. Okay, so we're going to fill it in right here into our ice chart. So you set up an ice chart here, and we're going to fill in the change using our coefficients in front of our balanced equation. So we're starting with 2 all across here, and then the change is minus x. The reactants are disappearing at a change of minus x, and the product is appearing at a change of plus 2x. So that your equilibrium concentration, you just simply do initial minus change, so 2 minus x, 2 minus x, and then 2 plus 2x. And you fill it into your KEQ expression. Okay, and the KEQ is given here. Okay, So they're just asking us to solve for x. So this looks like a very complicated math problem here. But this, according to the scenario, whenever you have both the top and the bottom squared, you can take a shortcut and square root both sides. Okay, so notice everything is squared. Okay, so when you do that, so remember, feel free to pause the video at any time if you need more time to copy down the answer. You should be writing down the example solutions on a separate piece of paper just to like walk through an example so that it's sticking in your head more. Okay, so I square rooted this side and I square rooted this side. Okay, and you get, so when you square root something that's squared, you just get what's under here, because if you look at it, you're multiplying 2, this exponent 2, by 1/2. So you end up with just 1. Okay, so you get 2 plus 2x divided by 2 minus x, and then you just simply solve for x. So you're going to crisscross, this is over 1. So 2 plus 2x equals 10.72 times 2 minus x. Okay, and then you use distributive law, so 10.72 times 2, 10.72 times negative x. Okay, so you're just opening up the bracket, equals 2 plus 2x, and then we're going to collect like terms, so all the x's go on one side. So I'm going to bring this negative 10.72 over here to make it 12.72x. 21.44 minus 2 gets you this, and then divide both sides by 12.72, and I get 1.53 moles per liter. Okay, so once you solve for x, you just simply go up to what we set each concentration value as. So H2 and F2 were 2 minus x. So we're going to plug in what we solved for x into that expression and solve for x. And HF was 2 plus 2x. So you just simply put it in and you solve for x. And you solve for the concentration, I mean. Okay. So you can double check by substituting these equilibrium concentration into your K expression and solve, and you should get the value of K. Okay, you do not have to double check it though, it's just for your own knowledge. Okay, and as you can see, you do get the value back, so you know you're correct. Okay, scenario number 2. So we're going to use the assumption to ignore the change in equilibrium. So we're going to talk about the assumption 100 rule now. So you can ignore the change x, assuming it is so small that it can be negligible, if and only if the KEQ is so small compared to the initial concentration, so that very little of the initial concentration is converting into the product. Okay, so I'll show you what I mean in a second. So basically, you're taking your initial concentration of what you have, dividing it by KEQ, and if you get something way greater than 100, that means your assumption is good. Okay, so that's what we're going to be checking to see if we can ignore the change in x. Okay, so I'm going to take you through this example. Carbon dioxide decomposes into carbon monoxide and oxygen. Calculate the concentrations of all entities at equilibrium. If we start off with 0.25 moles of CO2, placed in a 1 liter closed container and heated to 2000 degrees Celsius, and the KEQ is given as this. Okay, so I'm going to take you to my document camera for a second. Okay, so here we go. So you have your equation here. So I set up the ice chart. They gave us the initial concentration of CO2 in the question. Okay, and we started off with no product, so 0, 0. Okay, and then we're going to put in the change. So you're looking at the coefficient in front of your balanced chemical equation to figure out the change. So this is minus 2x here. This is plus 2x, and this is plus x. Okay, and then for E, the equilibrium concentration, you're simply taking I, adding to the change. So 0.25 minus 2x, 0 plus 2x is 2x, 0 plus x is x. Okay, so from here, you're going to plug it into your KEQ expression. So KEQ is the concentration of CO squared times the concentration of O2 divided by CO2 squared equals 6.40 times 10 to the negative 7. Okay, and then you're going to plug in the values we just found. So CO is 2x squared times O2 is x, and we're dividing it by CO2 squared. So CO2 is 0.250 minus 2x, all in brackets, squared, and we're making that equal to the KEQ value that they gave us in the question. Okay? Okay, so ignore the stuff in red right now. You just want to write down what's in black. And if you want to pause the video at any time, like I said, feel free to do so. Okay, so as you can see, if you want to use a different color, we are going to assume that this minus 2x is very small, so you can ignore it. Why are we assuming that? You'll see in a second, because we tested our assumption law. So this looks very complicated to solve, but you can use the assumption to ignore the change in x. So here's the assumption down here. So we're taking the CO2 concentration initial, and we're dividing it by the KEQ value that's given. So these two values are given to us. So notice the initial concentration of CO2 is way bigger than the KEQ value. When you divide it, you get a number way bigger than 100. So because of that, we're assuming that very little of the amount of CO2 given is going to turn into the products. So that's why you can ignore this change, okay? So because it's greater than 100, yes, we are going to ignore the x. So the assumption is valid. Okay, so we're going to plug it in right here. So we're going to ignore this minus 2x. So right here, I rewrote the bottom here without the minus 2x. Okay, and 2x squared times x is 4x cubed. Because x squared times x, you just add the exponents here to get you 4x cubed. Sorry, there's a mistake there. This is supposed to be a bracket around here, okay, because this 2 is being squared as well as this x. So it's going to be 4x squared times x, which is 4x cubed. Okay, and then 0.250 squared is 0.0625, and then equals the KEQ value here. I'm putting it over 1 so I can crisscross. Okay, so I get 4x cubed equals 0.0625 times 6.4 times 10 to the negative 7. Okay, so x is going to be this times this divided by 4. And then taking it, once you do that, you get 1.0 times 10 to the negative 8, and then taking it to the cubed root of that. Okay, and you should get 2.15 times 10 to the power of negative 3. Okay, so as you can see, there is a lot of math in this first example. So you do have to, there's going to be a lot of practice this week. Okay, so this x value we just solved for is the value of O2 if you look at our ice charts. Okay, so we just solved for O2. Now we have to solve for CO, so we're simply going to take 2 and multiply it by the value of x. And we're going to solve for CO2 by doing 0.250 minus 2 times the value of x. Okay, so I'm going to do that down here. So CO is 2x, so 2 times the value of x, which is 0.0043 moles per liter. Okay, and CO2 at equilibrium is 0.250 minus 2 times 2.15 times 10 to the negative 3, and you get that, 0.246 moles per liter. Okay, so now we're going to check our assumptions. So we're going to see, did it actually go down a little bit? And you can see there's a very little difference between 0.250 at initial and the equilibrium concentration. So we're going to check our assumption and make sure it's less than 5% of a difference. Okay, so I'm going to flip the page here. So to check the assumption, I'm going to take 0.25, subtract 0.246, and I get 0.004. And if you divide that by your initial, you get a very small percentage, which is less than 5% difference. Okay, so therefore our assumption is valid. All right, so that's example number 1. So we are now going to do an even more complicated example. We are going to go to scenario number 3, which is assumption is rejected. Okay, and now we're going to use the quadratic formula. So let's go back to our PowerPoint here. Okay, so here we have Br2 gas forming 2Br gas. And they gave us the initial concentrations of Br2 and Br. And they said calculate the concentrations of these species at equilibrium. Okay, so we are going to set up an ice chart. These are what was given. What's the change? Minus x plus 2x. And at equilibrium, it's 0.063 minus x and 0.012 plus 2x. Okay, so you plug it into your K expression. So Br squared divided by Br2. And we're going to plug in these equilibrium values into our expression. Okay. So what we're going to ask ourselves is, so we have to solve for x here. Are we able to ignore x? So we're going to take the initial concentration that's given, which is 0.063, and we're going to divide it by the K EQ that is given in the question. Okay, 1.1 times 10 to the negative 3. So it is not greater than 100, so therefore you cannot ignore x. Okay, so what you have to do is you actually have to solve it without ignoring this plus 2x. So it's going to be a lot more math. So we're going to take this bracket here and square it. So 0.012 squared is 0.000144. 2x squared is 4x squared. And then you have to do 2 times this times 2, which is 0.048x for the middle term. Okay, equals, and then I took this number and I multiplied it by this. So I crisscrossed, right, to get me this. And then I'm going to collect like terms, so put all the x's together and all the numbers together. So eventually what our goal is we want to get it into the format ax squared plus bx plus c equals 0, so that we can use the quadratic formula. And that is the quadratic formula here, which hopefully you guys are familiar with from grade 11 math. Okay, so once you solve, you can either solve by actually plugging in the value for B and going through the math, but which I'll show you. I actually did it on paper as well, so I'll show you that. But I believe that is the okay. So once you solve for x, we are going to plug in that x into the equilibrium concentrations and see which one is the correct one. Okay, you cannot have a negative equilibrium concentration, so that's why the correct value is this one. Because if one value gives you a negative concentration, then it's not correct. So I'm just going to switch over and show you what I did on paper. So just 1 second here. Okay, so here I just walked through solving it. Okay, so if you're lucky enough that you can plug it into your calculator and get the value for x right away, then you do not have to do all this part, but I just showing you the calculation I did using my A, B, C values. Make sure you take note of the sign in front when you're plugging in, because that could mess up your whole answer. So in this case, B is positive, okay, C is positive, and A is positive. Okay, and you have to go through it plus, so negative 0.0491 plus this divided by 8, and then another time negative 0.0491 minus this to get your two answers. So as I said here, negative 0.01 does not work, but the other one does, to get you two positive values for concentration. Okay. All right, so let's go back to, we're going to do another example here. Okay, so suppose that hydrogen fluoride gas, HF, is synthesized by combining 3 moles of hydrogen gas and H2. Oh, I think there's something missing here. So you're supposed to add and 6.00 F2 in a 3-liter sealed flask. So the KEQ is given as that. Okay, what are the concentrations for each gas at equilibrium? Okay, so we're going to set up an ice chart with the initial concentrations given. Okay, so I want you to try this on your own, set up an ice chart. Okay, pause the video, and then I'm going to take it up. Okay, so here we go. So they gave us H2 is 3 divided by 3 moles divided by 3 liters is 1 mole per liter. So that's our initial for H2. For F2, it's 6 moles divided by 3 liters is 2 moles per liter. And then there's nothing in the product. And then our change is minus x plus 2x to get you 1 minus x, 2 minus x, and 2x here. And then we're going to plug it into our KEQ expression. So HF squared divided by H2 times F2 gets you this KEQ value here that they gave us in the question. Okay, and I'm simply plugging in what's highlighted into my expression. So 2x squared divided by 1 minus x times 2 minus x. Okay, and your goal is to get this into this form so that we could use the quadratic formula. Okay, so I'm just simply distributing this to get me 4x squared on the top divided by 2 minus x minus 2x plus x squared. And I'm simply going to simplify this to make this 115 on this side. Okay, and then I'm crisscrossing. So 4x squared times 1 is 4x squared equals 115 x squared. So I'm going to multiply 115 by all of this. Okay, so that's shown right here. So by the way, we did not ignore the change in x here because I'll show you the assumption rule over here. If you check the 100 rule, F2 initial divided by the KEQ. So you always have to take the largest concentration of your initial divided by KEQ, and you get something less than 100, so you cannot ignore x. Okay, so I'm just going to show you the continuation of this on the next page. So you get 111 x squared minus 345 x plus 230 equals 0, and you use the quadratic formula to solve for this. Okay, so you get this or this, and then I figured out that you can't have the bigger number because when you plug in that bigger number into 1 minus x, you would get a negative, so that can't be possible. So we're going to use the smaller number. Okay, and you get this value here for H2 at equilibrium. Okay, and HF at equilibrium is 2 times x, so 2 times 0.968 to get you 1.94 moles per liter. And then finally, F2 at equilibrium is 2 minus x, so 2 minus 0.968 gets you 1.03 moles per liter. Okay, so this was a lot to take in. So you do want to practice these questions here. Okay, and we're just going to go back to the PowerPoint. So make sure you practice. And I'm going to give you one more question to practice on your own. And then I'm going to take it up. So this is not included in your notes. So if you want to write this down. Okay, so the question is, if 0.500 moles of N2O4 gas is placed in a 1.0 liter closed container at 150 degrees Celsius. Remember when they give you the temperature is irrelevant? They're just telling you that's the value of KQ at that moment. What will the concentration of N2O4 gas and NO2 gas be at equilibrium? And they gave us the value of K. Okay, so this is an example of rejecting an assumption about X. So here I'm going to set up my equation. N2O4 gas forms 2NO2 gas. Plug in your initial that they gave us. We don't know what the product is, minus X plus 2X. You get that. Okay, and then you do your KQ expression. Okay, and you plug in your values here. Okay, so I'm just going to check the assumption here to show you that you cannot ignore X. N2O4 0.5 divided by 4.5 is less than 100, so we cannot ignore X. So we have to actually go through and do the quadratic formula for this. Okay, so I'm going to stop there, and I'm going to ask you guys to try this on your own, and then at the next lesson, I'll post the answer to this. Okay, so just be aware there is a Chapter 7 quiz on Friday of this week. Okay? Okay, take care, guys.